History of Vector Analysis, Episode 8, Quaternions, Part 2. You are here. Hey, it's old Doc Goller. Welcome to the second half of my episode on the algebraic properties of quaternions. Last time we showed that quaternions added and subtracted okay, but we ran into a problem with the commutative property of multiplication. Specifically, we found that using Hamilton's rules for multiplying the ijk terms, it resulted in the fact that quaternions do not commute. That is, q1 times q2 is not equal to q2 times q1. Then, I argued, we found something that is perhaps even a little stranger. A simple change in Hamilton's ijk rules would have made quaternions commute. Specifically, all we had to do is define j times I equals plus k instead of minus k. But Hamilton didn't do this. Why not? Okay, sometimes the only way to go is forward. So, on to the associative property. By the way, I want to state that neither Crow nor anyone else I know of explicitly worked through the math like I'm going to do here. This is all that proof is left to the reader type stuff, which I doubt any reader in history has actually ever performed. I certainly never did before I did this. Crow especially did not consider modifying Hamilton's ijk multiplication rules to see what happened, nor has anyone else that's written a book about it so far, at least one that I found. So, you're welcome. All right, the associative property of multiplication for quaternions. Now things really get messy and the font size becomes downright unreadable on the screen. The charts, if you actually want to study them, are on the Old Doc Goller website. Okay, here are your three quaternions, and the question is, does the quantity q1, q2 times q3 equal q1 times the quantity q2, q3? We'll do the left side first, starting with q1 times q2, which yields these 16 terms. You evaluate the ijk's, and then you group by the ijk coefficients. Here you go. The next step is to evaluate this product when multiplied from the right by q3. 16 times 4 yields 64 terms. Here we go. Multiply out the terms. Step 2. Evaluate the ijk's. Step 3. Reorder the terms in ijk order, 16 in each group. Let's call the result box 1. Now let's evaluate the right side, beginning with q2, q3. Hopefully you know the drill by now. Here are the 16 terms of the product. Here they are again with the ijk's evaluated. And here they are with the terms reordered. Next, multiply this product by q1 from the left. Here are the 64 terms. Here they are again with the ijk's evaluated. And here they are regrouped by axis parameter. So now the question is, do the terms in box 1 match up with the terms in box 2? As with the commutative analysis, the only organizational break we have is that the 16 real terms in each box must correspond to each other, and the same for the I, j, and k terms. Okay then, here are the 16 real terms from box 1, and here are the 16 real terms from box 2. Do they match up? Well, I will save you the tedium and simply display this. Yes, lo and behold, all of the terms do match up, including the all-important plus and minus signs. Was this expected? Well, we got this far before with the commutative property. The reals matched up, but then the i's, j's, and k's didn't. So, we continue. Here are the 16 I terms from box 1 and box 2. Do these match up? Drum roll, please. Wow, they do. Are we on to something? Here are the j terms from the two approaches. What will happen? Are you on the edge of your seat, as perhaps Hamilton was? Yes, the j's work too. Here are the k terms. We're feeling pretty good right now, right? Dare we hope? Yes, the k's match up as well. This means that quaternions are associative under multiplication. Should we be surprised given that they are not commutative? Well, I will simply state without proof that none of this works out for pentonions, hextonions, etc., nor would it work out for triplets. Only real numbers, complex numbers, and quaternions, and to a partial degree octonions, have any sort of an associative property. Spoiler alert. In future episodes, I will show that vector operations, the dot product, the cross product, the Laplacian, are also not associative. So yeah, in retrospect, this turns out to be a kind of a big deal. Hamilton himself certainly thought it was a big deal. Previously, I stated the IJK multiplication rules that he invented/discovered, but if you go and look up quaternions, you will always find an additional rule, that is IJK equals -1. Now, in fact, this is redundant. If you have the other rules, you don't really need this one. I think he included it to tacitly make the statement that quaternions do have the associative property of multiplication. Okay? If you evaluate IJK from the left, you get k squared. If you evaluate it from the right, you get I squared. Now, k and I are not the same, but k squared and I squared are. And that, troubled physics majors, is how you get quaternions to obey the associative property. Nothing to it, right? But we have to ask, or at least I have to ask, would quaternions still be associative under multiplication if we change that IJK rule so that IJ equals JI equals plus K? If so, then we could get quaternions to satisfy both the associative and the commutative properties. Sorry, I can't let it go. Well, the easy thing to do would be to consider Hamilton's additional rule with the new product rules. Since IJK is cyclic, IJ equals plus K and JK equals plus I, and so the anti-cyclic rule doesn't come into play, and so there is no difference. Is this good enough to draw the conclusion? Well, let's double check the general case anyway, right? No big deal. First, we consider the left side quantity Q1, Q2 times Q3 from the right with the new rule. So first we consider Q1, Q2, then we multiply in by Q3 from the right, we evaluate the terms, we use the new anti-cyclic term to evaluate the IJKs, and then we regroup. Now the right side. First, Q2 times Q3 with the new anti-cyclic rule. Then bring in Q1 from the left, crank out the terms, evaluate the IJKs, and regroup. Now, do the boxes match up? Well, I'm just going to show you the results this time. The real terms do match up, although there is a certain unbalance in the terms. We get one positive term and 15 negative terms, but we could probably live with that. The other sets of terms, the i's, the j's, and the k's, are not so well behaved. In each case, 12 of the 16 terms match up, but 4 do not. They have the wrong signs. To be considered associative, all of the terms must be the same. So, the bottom line is that while quaternions may be commutative under multiplication with the anti-cyclic rule JI equals plus K, they would not be associative under these rules. Hold that thought. Okay, we aren't finished yet. What about the multiplicative identity for quaternions? Is there a quaternion Q sub mi such that Q times Q sub mi equals Q for all Q? Well, probably. Let's consider Q sub mi equals 1, essentially. Okay, because things have gotten a little weird, let's go ahead and multiply it out just to be sure. You get this, which is in fact Q for an arbitrary Q. So, yes, there is a multiplicative identity for quaternions, and it doesn't matter what anti-cyclic rule you pick for cross-multiplying the IJK terms. Finally, the inverse property. This again will be a property that modern vectors will not possess, so let's set up some compare and contrast functionality for later, and let's show that the inverse property does exist for quaternions. We begin, as always, by asking the question, for all Q in the set of quaternions, is there also a Q inverse such that Q times Q inverse equals 1? And as usual, we will begin by considering the inverse of Q as being equal to the reciprocal of Q. We again run into concerns about the IJKs in the denominator, which may or may not be a problem. We follow the procedure from complex numbers and try multiplying the reciprocal of Q through by unity, where here unity is cleverly chosen to be the complex conjugate, or rather the quaternion conjugate, over itself. The numerator is straightforward to evaluate. The denominator is a bit messier, but it does reduce to a real number if we assume that Ji equals minus K and the other anti-cyclic rules of Hamilton apply. I'm going to come back to this in a moment. For now, though, let me just state that because we can express the reciprocal of any quaternion Q as a different quaternion in the set multiplied by a real constant, we may conclude that the inverse property for quaternions is defined under multiplication. This also implies that division is defined for quaternions. For me, though, the nagging little question remains. Would quaternions possess an inverse property under multiplication if we used the different IJK multiplication rules, the one where Ji equals plus K? This requires a deeper look at the math we did on the denominator where we multiplied Q by Q star. Here are the usual steps. First, we multiply out the terms. Then we evaluate the IJK coefficients, here using the Hamiltonian Ji equals minus K anticyclic rules. Then we regroup. Okay, we can see that the real part is non-zero, and in fact, all of the terms are positive. The terms proportional to I, J, and K, however, all cancel out in pairs, one positive and one negative. So the question becomes, are these term-by-term cancellations in the IJK components due to the chosen anticyclic rule? I will just consider the I terms in what follows. The first two terms, minus AB and plus AB, can be traced back through the math like this. In both cases, the signs are due only to the signs of the terms in the original quaternions. These terms do not refer to the cyclic or anticyclic rules at all, so they would cancel out either way. Now let's look at the other two terms, the CD terms that are proportional to I. Both of these do consider the cyclic-anticyclic rules. There are multiple minus signs that must be considered, but the final sign of the first CD term is due in part to the fact that JK equals positive I. The final sign of the second term is due to the fact that KJ is equal to negative I. This is the Hamilton-chosen anticyclic rule. If this rule were different and this were equal to plus I, then these two terms would not cancel. This, in turn, would imply that the inverse property for quaternion multiplication would not be properly defined, and neither would quaternion division. If you'll pardon my pun on the novel and movie title Sophie's Choice, Hamilton's discovery of quaternions in 1843 came not only after many years of struggle and a lot of really tedious math, it also came after what must have been a horribly difficult choice for such a metaphysical man searching as he was for truth in mathematics. He could allow quaternions to have the associative and inverse properties, but only if he sacrificed the commutative property. That's a big deal. Okay? He made his choice. He moved forward, championing quaternions as his number one priority for the remaining 20 years of his life. Historian Michael J. Crow makes the following statement about the significance of this move. Quaternions were the first well-known, consistent, and significant number system which did not obey the laws of ordinary arithmetic. His discovery may be compared to the discovery of non-Euclidean geometry. Both discoveries broke bonds set by centuries of mathematical thought. Having said that, Crow goes on to state, in the period immediately after the discovery, quaternions were criticized because of the abandonment of the commutative property for multiplication. It is an interesting historical speculation in this regard as to what would have been said of a system in which the commutative and associative properties failed, and which division was in general impossible, and moreover in which there were two different types of multiplication defined. Crow is, of course, referring to modern vector analysis. Hamilton's Lectures on Quaternions were published in 1853, a full decade later. This tome is a massive 737 pages, not including a 72-page table of contents. Hamilton had a variety of personal demons attacking him now, but he put an enormous amount of work in between 1843 and 1853. Some of the terms he introduced in this work were scalar and vector, unfortunately along with dozens and dozens of more arcane terms. And of course, this work contained lots and lots of metaphysics. All that stuff about how quaternions would do for algebra and time what Euclid had done for geometry and space. Hamilton's writing style was terse and cryptic. His enormous stature meant that it couldn't simply be ignored, but even the best professional mathematicians of the day found it almost impossible to read. Despite his fame, The book sold very poorly, as did a second authored book on the subject, Elements of Quaternions, published posthumously in 1866. Hamilton was blown away by the internal consistency and the structure of quaternions. He thought that this was the greatest discovery of his career, and he spent the rest of his life trying to develop and propagate their use. His priority was always on the philosophy. He thought there might be some practical physics and engineering applications out there, but he put little effort into investigating them. While others recognized that there was something there, very few of them were as enamored with quaternions as Hamilton was. Few bought into Hamilton's view of quaternions as fundamentally underlying reality. Okay, as noted, he did not write very clearly. Even his mathematical arguments were difficult to follow. Crowe researched a number of papers on the subject of quaternions written before Hamilton's death in 1865. He counted a total of 150, of which 109 were written by Hamilton himself. But quaternions as a field did take root in several countries, and in fact there were some who did recognize practical applications for them and worked to develop them. In the next couple of episodes, I will discuss some of the gems buried in Hamilton's tome. I will begin with the way that Hamilton divided his quaternions up into a real part, which he called a scalar, and the triple imaginary part, which he called a vector. Okay, we're done for today. See you next time.